Yes.
Sorry.
So this speech is going to be about the transfer of technology from the oil field and into what I have named medium deep geothermal drilling or testing. And it's about the South Scandinavian basement. I think everybody here will know the difference pretty much between sedimentary rock and basement in terms of its drillability. The difference is almost in cases like the difference between wood and steel. So when we look at technology and technology to transfer, the most interesting part is the basement. And the South Scandinavian basement that we have under us here is one of the toughest ones to drill. So if we can do that, then we should be good. I've spent my career pretty much since the late 80s in development of drilling technology for the oil and gas industry, mainly in the UiS, but as Norway was becoming one of the biggest customers to new technology and advanced wells, of course, my job was to move the technology over here. The way of sort of conceptualizing the challenge is put up here as an Asplan graph, and what it's having on its y-axis is the market cost for energy. Now this scale shouldn't be thought too much into because it's quite advanced, because there are summer prices, day prices, night prices, and so on energy. So you can't really use it for much. The idea, the important part is the lower the unit cost, sort of the more will be or the more expensive power is, the more geothermal energy will be utilized. So it's simply that's really all it's about. So what we want to look at is what can we do with new technology to make the pricing for geothermal energy so low that we can extend to the full potential of the market. And this is pretty much the same number as was presented earlier on in the potential for geothermal energy. So, but to get there, as also been covered before, we need to come down in price. We look at pretty much just from the drilling experience and also from the oil field, a curve going a little bit like this. Well, first of all, the gradient is here. This is the cost curve. And as we get deeper, it's getting a lot more costly. It takes longer to get out of a hole, bigger rigs, more expensive, more crew, 24 hours operations, expensive fluids, lots of it. So there is an area here from 2,500 meters and up to, depends on where you are in the world, of course, say 3,000-4,000 meters. That's sort of in the yellowish area. We don't spend too much on time on that, but there is an area here where we have a reasonable chance of predicting the cost and not going sort of totally overboard on the cost and technology side. So we wanted to look at applying our technology and the latest and greatest in offshore drilling technology, onshore for that sake, oil field technology, to see what we could do and sort of what our position was right now in terms of being able to get the cost down. So this is the fastest tool we have. It's the, let's see, took a couple of them in a row there. Yeah, there we go. That's the drill bit that is typically preferred to be used. It's a PDC bit. It's very hard, very efficient, and it drills pretty much anything. So it's often the tool of choice. It's in one piece, so things rarely fall off it. And it has mainly one aspect to be aware of, and that is the fact that, of course, this is lowered to bottom and we put a weight on it to get depth of cut. That means there are two factors that controls how much torque is used to rotate this bit. That is friction, and it's the cut. And friction is typically as much as 60% of the energy. And that's, of course, meaning that balancing the load of this bit against the bottom of the hole is very critical to its efficiency and also to its life. Because regardless how good these diamonds are, even the best quality that is on the picture here, if you overheat it, if you get towards 500, 600 degrees from friction, it will start dulling. You can't get away from that. And that makes the cutters weaker as well. So that's what we are dealing with. The success of Tomax have been to get a good grip of the dynamics in the drill string, because the drill string here stretches from 1 to 10 kilometers, and here is the drill bit we discussed. And so we are dependent on having this interface balanced as well as possible, or as perfectly as possible, and that's a pretty difficult task. It's almost impossible because of the likely harmonics in the axial direction and the torsional direction of the drill string. So what Tomax have done with cooperation from academia is to model the drill string with modern tools times and times again until we finally defined it so well that we could make a regulator that would counteract the effects in the drill string, so we would have a more optimized loading on the drill bit. The results of that is typically 40 to 60% ROP improvement. In this, in the geothermal area, that's maybe even not the most interesting part. The most interesting part is that we get far more distance per bit, because when the efficiency improves, the wear goes down. It's the first and most important effect of improving efficiency is to reduce wear on these kind of drill bits. So, and of course, these things creates a lot of value for the operator, the drilling oil field operator in our case mainly. We also do geothermal wells, but it's mainly oil field. And that have cost us sort of to drill so far 200 million meters or 12,000 wells with this technology, average depths 4,000 or 5,000 meters. So the background experience on this technology is great, and long, 15 years approximately. So what we wanted to do in our test that I'm going to talk about is to take two of these new drill bits and test them with and without AST in the gneiss just below us here, below the fillet, down in the real Scandinavian basement, and see what performance we could get out of this, I name it, great technology, in combined with a PDC bit in the toughest challenge there is. So this is the unit itself here on the catwalk on Ulrik. In this case, we put sensors in it to measure its workload, and we had also temperature for obvious reasons in this case. But that's how that looked when we took it in. Here's one important element: drilling in deep, drilling in hard rock in particular is a little bit like flying an aeroplane. If you do something wrong, the consequences are sort of end of the game. So you have to be monitoring and literally almost have two pilots side by side to monitor the data all the time, because if anything starts drifting, you will get into a situation you can't recover from, and the well is lost. The rock is so hard, sidetracks are very difficult, or at least they are very costly. So therefore, monitoring is important. And this test here I was responsible for, so then I was the one to decide what monitoring we would have. And this is a graph a lot of people have seen in the oil field on vibrations. That is a graph that we made in the 90s. I was part of that, based on our access to accelerometer and MWD tools. And it's not very accurate. And accelerometers are not very useful for this purpose. So be careful about applying the accelerometer data. That's the important takeaway from this session. The accelerometer reflects what's going on at MWD, and the accelerometers are highly biased by the freedom of motion or the freedom of moving. So the most critical direction in the drilling with a PDC bit is the axial, but there's no freedom in the axial direction, so you won't see what's going on. There is one very good measurement, though, that is almost free, and that's to continuously monitor what we call in the industry the mechanical specific energy. That's how much energy you are putting in to remove a certain amount of rock. And by putting sensors that monitors your ROP and your weights, you could also put RPM on there. You can normalize the energy being put into the system, so you can know at all times what energy is being consumed to drill the rock. And it's updated continuously. So you'll have that number in front of you when you're drilling. And that's what we had when we did this test. Luckily, that was at Ulrik, so we had 50 hertz measuring, so we would have it going all the time. If that measurement starts moving upwards, you're spending more energy to drill, then you're in trouble. That shouldn't happen. So anyway, first bit we ran into 1100 meters in the gneiss. It looked like this, so now you can imagine sort of from what I said, mechanical specific energy is here. And we started out and we saw a relatively promising start, but suddenly things started moving up. We needed more and more energy to drill. So normally you would pull out the hole or stop here. Well, this was 1 hour. Anyway, we tried to stop and save here, see what we could do, couldn't do anything. The bit was destroyed, and after 1 hour we had to come out of the hole and the bit was damaged. And that is an expensive bit, and it's an expensive trip out of the hole. So this was a stiff system, no AST, nothing taken care of the motions in the axial direction. So if this bit, for example, started bouncing or anything down there, sort of it will self-destroy. Not because of the impact, but because of the heat. Because when that gets a high loading in the axial direction, all energy goes into friction to overcome friction. So that's the dynamics of it. So we applied our regulator, and this is what it looks. We got the efficiency improvement. So we got a higher efficiency, and we started drilling, and we maintained the bit sharp. So that was good. We tried a little bit of different parameters, and oops, we saw the energy was coming, the mechanical energy was coming up, the ratio, so efficiency was going down. So we went back again to the original parameters, and we could basically keep going. So this was in one way a success. It made the bit last longer, and it improved efficiency. And this is the bit coming out of the hole afterwards. But the speed was useless. We drilled with 1.5 meters per hour. And that's too slow. What happened was, from that data, was when we tried to put weight on it, we put so much friction into the system that it would start wearing. That's why we had to come off again directly. So what we realized from this one, and it probably wasn't going to get us any Nobel Prize because probably a lot of people know it, but the igneous rock, crystalline rock, has a very high friction coefficient of friction compared to sedimentary rock. Probably 0.6 against the diamond cutters. So that was the reason. That's why it produces so much heat immediately when it's loaded. And of course, the ambition here was to go with fresh water. So that didn't help the situation. So in conclusion, learning PDC bits, although being the best there is, when the rock gets tough enough, they they are not suited for the job. And it's not because the rock is hard, it's because of the coefficient of friction. Yep. 2 minutes, yes. So we looked at ways of solving this, got the tip from Ove Hegland, water-based or drilling with water in granite. Roller cones will do fine. This is not Ove on the picture, but it's one of his jobs on Norsk Retningsboring, I think, in Trøndelag. We looked at a little bit closer into the roller cone data. The roller cones are well known for failing, or not failing, but you have to have very short intervals because of the bearings. And the bearings is the weak part. And you can see why this is the downhole pattern measured by strain gauges. So this is what the bearings really see. This is what you see at surface for weight. So the risk of damaging the bearings is very high. So what we see is when we run the regulator, the AST, with the roller cone bits, we save the bearings. So we looked at that, if that could be the possibility, and we went back to have a look at some results from Germany, and we saw, or Austria, this is where we put the AST on roller cone bits for other reasons. And when we looked at it, we had the efficiency improvement and the extra speed, and we always did it in one run. These are the offset wells, doing 2 runs to get to the same distance, and they are slower. So we believe that in this case, and don't use too much of the scaling here, but we think in the hard rock, South Scandinavian basement, PDC is not a solution. Even if you're adding the regulators we apply, it's still not going to work very well. It's going to be too costly. But there is a chance, the way, based on what we've learned, where we can get down to at least 600 kroner per meter, and that is to apply rock bits and a regulator. We believe that a rock bit with this kind of a regulator will last practically forever. The bearings will last in the same range as the wheel bearings on a car. So the potential is there. There was a bit of learning that was kind of had no use, but we think we are on the right track to be able to lower cost considerably. Of course, this is only one part, but it's an important part. Everybody knows that in geothermal and hard rock drilling, sort of getting the cost down and the risk down is critical. This is just, since it was a geothermal well, this is the temperatures we looked at. So the static is 27, or at this depth it should be 21. This is the circulating temperatures, and that was the surface temperature. So this is at very high flow rates. We still manage to keep the fluid hotter than the surface. So even here we got quite a bit of energy out of the ground, at least sort of enough to prove that it would take some good circulation rates. So that's what I had. Thank you.
Thank you, Nils.